In this tutorial, we are going to discuss about momentum conservation, or angular momentum conservation to be specific. Angular momentum conservation can be observed in many aspects of our day-to-day life. Here, for instance, we can see it in the display in a figure skating at the Olympic Games. So in this tutorial, first we'll define what is angular momentum, and then we'll present experiments that the student can do to understand the principles, and we will conclude with a discussion of one application of the principle of angular momentum conservation. So angular momentum is the quantity of rotation of an object around an axis. It tells us how much rotational motion an object has. So the faster the object spins, or the harder it is to stop, the larger its angular momentum is. And so the angular momentum is defined as the product of the moment of inertia with the angular velocity. And the moment of inertia measures how difficult it is to change the rotational motion of an object. It depends on the object mass. So if it is very heavy, it might be difficult to move it, to rotate it. And it also depends on the positions from the axis of rotation. And the angular conservation, the conservation of angular momentum is stating that the angular here will always be conserved. So here, for example, we have two scenarios of a figure skating, where in this figure the arms are open, so the moment of inertia are larger, and then so the velocity is smaller compared to the velocity when the arms are closer to the body, because here the moment of inertia is smaller because it's much more closer to the axis. So that is what conservation of angular momentum is. And as an experiment that the student can do, we will place a rotating platform on the floor first, and a rather special location of about 2 meters in diameter would be required for this experiment, so that the student will have enough space, also like if they need to step down on the floor. And the facilitator can do the demonstration, or if a student can volunteer to try it, then they should be able to do it. So the person will therefore stand on the platform with their hands spread out horizontally, like in this figure. If there are mass, they could also hold mass at their far hands, the hands. So their body should be aligned such that the center of mass is right over the center of the platform. So we have the axis, so this is the rotator, the platform that can rotate, and this is the axis of the rotation. They can also spread their leg to be at the edge to make the moment of inertia even larger. Also, the platform can rotate about the vertical axis then, and then the person on the floor should take one of the arm and give them a spin, not fast, but not too slow as well. And from this experiment, they should observe that their rotational speed increases when they bring their arms closer to the body. So bringing the arms closer to the body, and also if possible the leg. So they will spin faster in this instance than when they have the arms spread out. So it's already explained previously, but we will have much more deeper explanation here, how to explain this? The angular momentum is conserved. So we have this equation that is like equaling stating the conservation. So I here is the initial state where we have the arm spread out. So the moment of inertia multiplied by the angular velocity is equals to the product in the situation where the moment of inertia and the velocity is in this when they bring their hands together, the arms together. So the situation is that the weight distribution from center changed in this scenario, so the moment of inertia is reducing. So if having this equality and moment of inertia in the initial state being bigger than in the final state means that the velocity in the final state should be larger than the initial one, and that explains the spin faster. Now, in this second experiment, we ask the student to stand on the platform, and the platform is set to be at rest at the beginning of the experiment. We will hand them a wheel that we have given a spin. So in this figure, this is the wheel. So it's like a bike tire, and the wheel is spinning, rotating about its axis, and that the axis is perpendicular to the axis of the platform they are standing on. So the person is to hold the rotating wheel with the rotating axis of the wheel to be perpendicular with delta here. And if we make an observation, we notice that the person will still remain static. And now, if we ask the person now to rotate the wheel such that its rotation becomes parallel to the axis of the platform delta on which they are standing on. So the hands will be, one will be at the top and one will be at the bottom. So the rotating axis, the rotation axis of the wheel will be parallel to delta. We should be observing that the person will start to rotate in the direction opposite to that of the wheel. And that is experiment 2. And how do we explain that? So initially, when the wheel is oriented such that its axis is perpendicular to the axis delta, the wheel's moment is 0. So, and also the moment of the platform or the person is also 0 about the axis delta. So the momentum the momentum of both is 0. So the person remains static. And when the wheels the wheels axis becomes parallel to delta, the angular momentum of the wheel is no longer 0. But since there need to be conservation of momentum, angular momentum, then the person will rotate automatically in the opposite direction as the wheel, and that explains the rotation in this situation. So one application of this principle of conservation of angular momentum is a gyroscope, the case of gyroscope. In Madagascar, we do have tangime. So if you play tangime, it will spin on the floor for some times, and it will stop at some point because there are some frictions in the surface. But if there is no friction, it will still continue to spin. So a gyroscope is a device. It can be used to measure or maintain orientation based on the principles of angular momentum. It works because the rapidly spinning object conserves its angular momentum, which keeps its axis stable and resistant to changes in orientation. So some smartphones are equipped with a small gyroscope inside of them, and since its angular momentum is always conserved, the gyroscope can use that information to measure and track movement precisely. For instance, if the phone rotates in one direction, the gyroscope can track what other motion should compensate for that, and use that information to check if there is any adjustment needed to correct for the image we see on the screen. And some technology in the phone can proceed to correct for that motion accordingly, or if the camera needs to be rotated at some direction to capture some image, so that the image that we have on the screen is much more visually appealing. So the gyroscope can act as a sensor that measures the device rotation and orientation in three-dimensional space. It works together with other sensors like accelerometer to track movement more precisely. And this enhanced motion information and improves the features such as gaming controls, virtual reality, image stabilizations, and automatic screen rotation. So that concludes this tutorial.